Okay, we are going to take a look today at topic 6.8, which is the enthalpy of formation. So we are going to take a look at what's called Hess's law, and we're going to be visiting Hess's law in multiple ways to figure out the enthalpy change delta H for our reaction. Now we are going to be using what are called standard enthalpies of formation. So we're going to talk about what those are and where we get those values from, and then be plugging it into our equation here, which looks way more complex than it actually is, okay? This is also on your equation sheet, so it'll remind you the biggest thing we have to remember is products minus reactants for this. So the enthalpy change or energy change for an overall reaction depends on the enthalpy change for the total bonds that are broken and formed in the reaction, as we saw previously when we were calculating using this method. Okay, where we were breaking bonds, forming bonds, and calculating their energy. Excuse me. So the energy it takes to form a chemical can be looked up on a table of standard enthalpies of formation. So let me show you what that table looks like. I'm going to be giving you a copy of this in class. There's a similar one in your textbook, but it's a little harder to read, honestly. So I'm going to give you guys this one. Now, this list, and I'm going to do this when I copy it for you guys, is actually two lists. It's not the best set up table ever because it's a little confusing. So it lists our elements in alphabetical order from their element name so we can find things easily, and it gives us 3 values for each chemical. Now, each of the values, we will use all of 3 of these eventually, but we're going to only focus right now on the first column. So these are called thermodynamic quantities for selected substances, and they're at 25 degrees Celsius or 298 Kelvin. So that means all the chemicals, all these values are related to each other because they're all measured at the same temperature. So we can compare them with each other. That's why they're called standard enthalpies or standard free energy or standard entropy. They have that little not sign, that little circle next to them. That's not a degree sign in the symbol. That's telling us they're all under the same conditions. They're measured under the same conditions. So a standard enthalpy of formation, let's take a look at just aluminum here. We've got 3 different chemicals, 3 values. We've got aluminum solid, regular aluminum, like your aluminum foil that you have at the store and that we use for our leftovers. So that has a value of 0. That means it takes 0 energy to form aluminum solid. Well, why is that? Because it's already made. It's in the earth. It occurs naturally as aluminum solid. You'll see that as you go down the list, the first element or the first chemical under each element is its regular elemental form. Something in its elemental form has a delta H of 0, which is really convenient. Now, if we go down here, look at bromine. Bromine by itself is not 0. So its most stable form, its elemental form, is actually Br2 as a liquid. That's one of our Hofbrinkel elements that comes in pairs, and it's a liquid, so that's where it's 0. If we turn it to a gas, that takes energy, so that value is going to be larger. You can see that here with calcium. The natural form of calcium is a solid, so that's going to be 0. To turn it into a gas, we got to put in energy, so it's positive 179. Carbon's an interesting one. The carbon in your pencil, the graphite in your pencil, is the natural form of carbon. To make diamond, we got to rearrange those atoms, and it takes some energy. To make carbon gas, it takes a lot of energy. So we got a lot of values that are positive, but we also have some negative values. Now, when we look at the negative values, those are mostly when we get into chemical compounds, right? We're mixing these with something else. So let's talk about how they get this value, or what this value means. So this aluminum, let's do aluminum chloride, AlCl3. That solid, okay, it is, actually I should write this a little bit differently. So if I wanted to write a reaction forming that chemical, I would take my aluminum solid and my chlorine gas, and I would balance my equation. I need 2 of those, so I need 3 of those. And this is the equation to form this chemical. So the energy it takes to form that chemical from its elements is negative 705.6 kilojoules. So 705.6 kilojoules are needed, or are, excuse me, not needed, are released when we form these bonds. Said that backwards. So we give off this much energy when we form bonds. Remember that bond breaking is endothermic and bond forming is exothermic. So this is an exothermic one because we're forming a chemical. So we've got a whole lot of these that are exothermic as we form those new bonds. A few of them will be endothermic because it just takes more energy in that particular case to form the bonds in that chemical. So for instance here we've got C2H4, so it takes more energy to break the bonds than it does to form the new ones, so we end up with 52.30 positive value. But that's what these values are really showing us, is if we form that chemical from its individual elements, what is the change in energy to do that? The enthalpy of formation. So now we talked about this list a little bit and what's available on here. Again, they're in alphabetical order. It does continue on the next 2 pages with our elements. Something to be aware of if you're looking for water, because we're going to see water a whole lot. It's not under hydrogen. It's under oxygen, which is down here on the 2nd page. We're going to see water. You'll see it as a gas and a liquid. So be careful with which one you're using there. That's the other thing. You'll notice we have different states of matter for chemicals, so we need to pay attention to those states of matter in our reactions. So, these are our values to form our chemicals. So any chemical that is a reactant will be breaking its bond, and we'll need its sign flip. So when we look at that data table, it's looking at forming those bonds. Well, reactants break their bonds. So all of these values, if I wanted to look at the energy to break these bonds, it would be the opposite sign. So on here, it's negative 705. If I wanted to break those bonds, it'd be positive 705.6. Okay, so we'd have to flip the sign. Now, we don't want to have to deal with flipping signs. So our equation does that for us. All of our reactants where we're breaking bonds need their sign flipped, and that's why we subtract. So you don't have to flip any signs, don't worry about that. We just need to make sure we subtract products minus reactants in that order, and it will take care of it for us. Okay? So a couple of things, as I said, they depend on their states of matter, so we want to pay attention to that. For instance, we can compare water as a liquid and water as a gas. It releases more energy when it's a liquid than it does when it's a gas, right? Gases need to have more energy to stay in that form. And then our things in their elemental form are 0. So when we see like O2 gas, we're going to be able to plug in a 0 for that. So we'll see examples of that. So let's take a look at one of these. How do we calculate this? So we've got our chemicals. They have coefficients. We're going to have to bring in those coefficients because when we look at these, their values are in kilojoules per mole of that chemical. So in forming 1 mole of that substance, if I want to form like 2 moles, I need twice as much, right? Or release twice as much energy. So we have to take into account our moles. And then we also need to make sure that we're doing products minus reactants. So here's what I do. I start from the right side and work my way to the left, so that I know I'm getting all my chemicals, I'm taking account for everything, and I've got an order to it, so I'm not missing anything. So our delta H value for our reaction, here's how I do it. I'm going to just set up my equation. I need 6 moles of water, so times the value for water, plus 12 moles times my value for carbon dioxide. And I'm going to multiply those out and then add them. And then I'm going to subtract my reactants. So I've got 15 moles of oxygen plus 2 moles of, I keep forgetting to write moles, C6H6. So now I've got it set up. I know what I'm referencing here. That pen is a little harsh to look at. Let me switch. So now we're going to plug in some values. Now, when we look at these, to save ourselves in terms of some space and writing a whole lot of things, we're going to be taking moles of our chemical and multiplying it by that chemical's value, which is in kilojoules per mole, which will allow the moles to cancel. So all of these are going to end up with kilojoules. So honestly, I'm going to leave out my units, which I know is hard to do. You can leave them in if you want, but everything's going to end up in kilojoules. So it kind of simplifies things. So I've got 6 times my value for water. Now my water is a gas, so I'm going to find water as a gas. We said was under oxygen, negative 241.82. And I'm going to add to it 12 times my value for carbon dioxide, which is under carbon. So carbon dioxide, gas, negative 393.5. And I'm going to find that value. Then I'm going to subtract 15 times oxygen's value. Here we go. Oxygen gas. Guess what? That's its elemental form. So it's going to be times 0. So we can get rid of that term. Plus 2 times C6H6. So I'm going to go back to my carbon. C6H6, and we want the liquid form of that. So here's my liquid, 49.0. All right, so now I'm going to simplify things a little bit. And I do this in chunks just to be sure that I can kind of check myself as I go. So we've got 6 times 2, negative 241.82. Plus, and I'm going to put this part in parentheses, 12 times negative 393.5, and that's my total for my products, negative 6172.92, and I'm going to round at the very end, so not in the middle. I'm going to bring down my subtraction, and then my other value. I've got 15 times 0, which is 0, plus 2 times 49, which is going to be 98. 0.0, because I do have that extra sig fig there. So we've got negative 6172.92 minus 98.0, and we get negative 6270.92. Okay, 6290 point, and we are doing some adding and subtracting here. So we're going to look at decimal places. This number has 2 and this only has 1. So we're going to round to 1 decimal place. So my answer is just going to be 0.9. And as I said before, our units are going to be kilojoules. So our delta H is negative 6,290.9 kilojoules of energy. So if we took this reaction, I could then write my delta H value over here. Say negative 6290.9 kilojoules, like we've seen before. So it's another way of finding our energy or enthalpy of our reaction. All right. It's pretty straightforward as long as you keep track of your products minus reactants. That's the key here. So again, I work from right to left, list everything so I know what I'm plugging into, and then start working with my numbers. Okay, and like I said, I like to chunk my calculations just to see where, if I do make a mistake, I can find my mistake easier. I'm not having to recalculate the entire thing every time. Okay, the other type of question we might see is it gives us, in this case, the delta H for our reaction for the following is negative. So delta H equals negative 1502.16 kilojoules. So we already have delta H. Well, what are we trying to find? We want to find the change in enthalpy of formation. So that little F means formation for Na2SO4. So we want to find the value for this one. Why do we want to find that? It's likely that that number doesn't have a value in our textbook. So if we look at it, it's aqueous. Here it's solid. So we don't have the aqueous value, so we're going to try and calculate it. Okay. Now, I did make one change on this. This was a typo. This first chemical is a solid. So I'm going to set up my equation, and then we're going to plug everything in and go from there. So delta H equals my products. So I'm going to have 1 mole of the Na2SO4 plus 2 moles of water. And I'm going to go ahead and put a little L there for myself as a reminder that it's a liquid. So there's my products minus my reactants. So 2 moles of NaOH plus 1 mole of H2SO4. Okay, so now I've got everything laid out. I know what I'm looking at. Now, I have my delta H, so I'm going to go ahead and plug that number in, negative 1502.16 kilojoules. And this is times 1 mole, so I'm just looking for, I'm going to replace that with X, because that's what I'm looking for, right? I'm looking for my variable. Now this is X plus 2 moles, so 2 times my value of water in a liquid. So I'm going to go to my oxygen section, sorry if that's a little thing, and water as a liquid is negative 285.83. So there's my products, there we go, minus my reactants, 2 times NaOH, and that's aqueous. So under sodium, there we go, NaOH aqueous, negative 469.6. Plus 1 mole times H2SO4, so H2SO4. Now, you'll notice here, this is another good example. Water wasn't under hydrogen. Most things are not under hydrogen. So if it's got a hydrogen in the front, it's going to be under the next chemical. So this is H2S, so sulfur. So I'm going to look it up under sulfur. And there we go. And we need sulfur. Oh no, this one is aqueous. My bad. So this is aqueous, not solid. So that's fine. I thought there was a typo there. All right, H2SO4. Oh, that's not what I wanted. I need the value. We already have that written. So our value for H2SO4 aqueous is negative 909.3. You'll notice I threw a parenthesis in there because I already have my plus sign. So that's just reminding me that it's a negative, separating those a bit so we can keep track. So now we're going to start simplifying things a little bit. I'm going to get the right side simplified, and then we'll do some getting our variable isolated and everything. So negative 1502.16 kilojoules equals, okay, we got 2 times negative 285.83. So X minus 571.66. And then we're subtracting 2 times negative 469.6. And then I need to add negative 909.3. Oops. So I've got that. Negative 1848.5. Now, I've got negative this value minus negative that. I'm subtracting a negative so I can add that and simplify this. So we're going to bring down my left side, negative 1502.16 kilojoules equals X. And let's see, I've got negative 571.66 plus 1848.5. And I've got X plus 1276.84. Whew. We're getting there. So now we've simplified both sides. Well, the right side mostly. We've got X plus this, and we've got our other side, so we need to subtract from both sides. 1276.84, 1276.84, and X is going to equal, negative 1502.16 minus 1276.84, and we get negative 2779 kilojoules of energy. Now, that is how much energy we need for, in this case, 1 mole of Na2SO4. So that's our kilojoules per mole for Na2SO4. That would be our value. So that's our enthalpy of formation, our delta H of formation for Na2SO4. Aqueous in this case. So to form an aqueous solution of that. Alright, so that's how we can find one of the missing values. If I had a coefficient that wasn't 1, then I'd just end up like 2x or 3x, whatever that coefficient is, and we'd have to do some dividing when we find our x. The big thing here, keeping track of those negatives and positives. That's where I see students make the mistakes, is not taking care of this subtraction properly. You'll notice that I keep my bright side in brackets here because it's subtracting this whole term, not just negative 15. So if I put subtract and then, or not just subtracting 15 times our oxygen, we're subtracting that plus our 2 moles of our C6H6. So this whole term is being subtracted. I see a lot of students, they'll simplify things and put, not carry that negative over. Okay, so if you need to distribute it or however you need to think about it, keep things in brackets, we got to keep track of those negatives. Okay, that's your biggest issue there. So I'm going to do one more with you guys just as a practice, so we can see just one more regular one. If you're good with this, try this one on your own, maybe pause and then come back and check it with me. Oh yeah, let's use our blue. So delta H, we are doing, again, products minus reactants. So we've got 2 water plus 1 carbon dioxide. And that's my products minus my reactants, 2 oxygen plus 1 CH4. My pen wants to die on me. All right, let's try this pen. It's working. Okay, so let's find our delta H. So 2 times water, in this case as a liquid. So find water as a liquid on your sheet. Should have negative 285. 0.83. And then we're going to add to that 1 carbon dioxide as a gas. And we use that up here, so that's going to be negative 393.5. So this is another good example. I put that negative in parentheses to remember it's there. So these are just reminders to myself so I don't lose any of my negatives. Now I've got oxygen here. It's in its gaseous form. It's in its elemental form. This term is going to be 0. So I'm going to take it out. So I'm just subtracting my CH4. And it is a gas. So that value from our table is negative 74.8. And we're doing it by 1 times 8 by 1 mole. So this simplifies down. We can go ahead and do some calculating here. So 2 times negative 285.83. I'm adding that to negative 393.5. And then I've only got 1 term here, so I'm going to go ahead and put that in my calculator as well. So then I am subtracting negative 74.8. Negative 890.36. 890.36. This has 2 decimal places, this has 1, this has 1. So I'm going to round this to 1 decimal place, so my 36 becomes 0.4 kilojoules. Alright, hopefully this is making sense. These ones are pretty straightforward. This is another way to, so Hess's law is basically ways that we can find the energy of a reaction. There's multiple ways. This is one, using our enthalpies of formation. And we're going to look at another one where we can add up reactions. We've also looked at adding our bond energies together to estimate our enthalpy of formation. So we got lots of, or enthalpy of our reaction. So we got lots of methods here. Let me know what questions you have, and have a great day.